Hello everyone! Welcome to Demystifying SQL Server I/O to improve your T-SQL performance. I'm super excited to be here today presenting to you for Data Platform Summit 2020. So my name is Andy Yoon. I am a Principal Solutions Engineer with SentryOne, soon to be SolarWinds, but I'm also a former DBA and developer. I've been working with SQL Server for quite a long time now, close to 20 years now. Former Microsoft MVP, and I've been presenting for a number of years now at various conferences all around the place. My contact information, of course, is up on this slide. I'm fairly active on Twitter, and my email box is open for you guys if you ever want to correspond and talk about SQL Server. So enough of that. I want to set the stage here and use an analogy to help explain all the different things we're going to be talking about today. So let's pretend for a moment that you're going to be moving house, okay? So think about that. And of course, with moving house, you have to pack up all of your different belongings. I have a lot of different belongings, so I have many different rooms to pack up, like my kitchen, my bedroom, and my home office. So these are many different tasks that are in front of me. And instead of just moving everything myself, I'm going to hire some movers, okay? I need some help. It's perfectly okay to ask for help these days, so I'm going to hire some movers, and then, hopefully those movers are going to help me out, right? But I still have to plan ahead. The movers can't do everything for me. I still need to give them instructions. So when my moving day comes, I've planned ahead. I've, tried to make sure I've made all of my proper preparations. However, on moving day, sometimes things don't go as expected. Things don't go as planned, right? There's always that unexpected thing that can potentially go wrong. And in the United States, at least, whenever you hire movers, it's not just a flat fee that you pay them. You pay them by the hour. Therefore, the more time you spend on your move, the more money it's going to cost you. That's why it's really, really important to be as prepared ahead of time as possible, so that way you're not spending an extra 2, 3, 4 hours worth of money on your movers because of poor preparations, right? And just like time costs you money when it comes to moving, in the world of SQL Server, time can also cost you money as well. Think about the last time you were on a web page and that web page was unresponsive, or an application that was unresponsive. Did you get upset? Maybe you got impatient. A lot of times these days, folks don't have a very long attention span. Therefore, they may wind up going somewhere else. If they're not able to shop online in your store, they may go to a different store, and they may get fed up waiting for things like your queries to return data. So let's translate this into a world of SQL Server. Think about these different questions. These are all questions or variations thereof of things that we as T-SQL developers have all faced over the years. It is my hope that after this presentation, though, that you will walk away with the knowledge that you need to be able to truly answer these questions from a SQL Server storage engine perspective, to better understand why SQL Server is taking more time than you expect. So to that end, I want to make sure that I'm upfront with you about today's agenda. First, we're going to cover a little bit of SQL Server internals. We're going to talk a little bit about the query lifecycle from a very high level perspective. And then I'm going to talk a little bit about data structures. And then we're going to talk about navigating heaps and indexes, okay? And then afterwards, the second half of this presentation is going to be all demo. I'm going to be walking you through different T-SQL I/O related scenarios. And to reiterate, the goal of this presentation is to help you understand SQL Server I/O, so that way you can understand query performance and query performance issues. This is a 200 to 300 level presentation, but anytime someone hears the word internals, they think, oh, this is insanely advanced content. And there is, again, some internals content, but please don't be scared by that, okay? I created this presentation in such a way that the information about internals is meant to be accessible to everyone, so that way you can be exposed to it, but not necessarily overwhelmed with it. So with that, let's get started. Chapter 1, Internals of the Query Lifecycle. So let's go back to the analogy that I had presented to you earlier. We talked a bit about the task of moving, maybe a discrete task like packing up my home office. And then we also happen to have a foreman, and that is the person in charge of the moving team. The foreman's going to come up with a game plan to tell the movers, okay, I want you to pack these certain things in this box, and maybe I want you to pack these certain things in this box, and so on and so forth. And then you have the movers themselves who will execute the plan as the foreman had instructed. Well, the analogy follows such that the task that you present to your movers is like the T-SQL query. Select from a given table, inner join another table, for example. And then the foreman, the person in charge, is akin to the query optimizer. It is up to the foreman to decide, okay, I want you to worry about the desk and you to worry about all the things on the bookshelf, for example, and so on and so forth. It's the foreman that's going to decide how the movers are actually going to execute my requested task of packing up my home office. And then the storage engine is akin to the movers themselves who are going to execute the instructions as given to them by the moving foreman. Okay? So that's kind of the high level analogy that we happen to have here. Now, let's break this down into how this works within SQL Server. I have a simple T-SQL query here, and the only important thing to understand is that we have table 1 inner join table 2. So this query gets passed to the query optimizer. The query optimizer does a bunch of work and comes up with an execution plan, which is then passed over to the storage engine. There's many elements to the storage engine, but the element that I want to focus in on today is something called the buffer manager. And it's the responsibility of the buffer manager to ask, are these data pages for table 1 and table 2 inside the buffer pool at this time? And the buffer pool, if you're not familiar with it, is RAM essentially. Okay, it's the area within RAM that SQL Server does a lot of its work. It's a caching mechanism essentially for our different data pages. So, are the data pages for table 1 and table 2 in the buffer pool? Let's assume in this context that the buffer pool is completely empty. This is otherwise known as a cold cache. So because there's nothing inside the buffer pool, the storage engine then says, okay, I need to retrieve the data pages for table 1 and table 2 from disk. So we will now retrieve them from disk, bring them into the buffer pool, and then we will process those data pages within the buffer pool after we've read them off of disk. Okay? So that's the first half of this. Now let's build upon that. Okay? We now have a second query that comes in. This is a request for data from table 1, inner join table 3, not table 2 this time. Of course, once again, this gets passed to the query optimizer, who then comes up with an execution plan, which passes it to the storage engine and the buffer manager. The buffer manager will now look inside the buffer pool and see, oh, I have data pages for table 1. That's great, but there's still no data pages for table 3. So for table 3 at least, I must once again go out to disk and then retrieve the data pages for table 3 and bring those into the buffer pool. Okay, so hopefully you can understand that particular bit of the life cycle and all of that makes sense. And that translates into logical reads and physical reads. Okay, so of course when we read off of disk, those are physical reads. And then when we're reading from the buffer pool, those are logical reads. But there's a relationship between the two of these. They're not necessarily independent events. And oftentimes I'm asked, which one should I worry about? Sometimes when I'm dealing with performance tuning scenarios, people will ask me, well, I don't care about the physical reads. I want to know about, or I don't care about the logical reads. I care about the physical reads. How many physical reads did this query do? Well, I'm not sure I actually care as much about that. I want to know about the overall logical reads that were required by this query, even though a subset of them may have been physical reads. And the reason for that is this, and let me use this following analogy to help explain that. So we're going to go back to the moving analogy, and let's pretend our movers have completed their task. So I'm standing in my home office now, and it is completely empty. This room that I'm in is representative of the buffer pool. Okay? And now I realize that I need something that has already been packed away. Maybe I need the power adapter for my laptop. So I know it's been packed away somewhere in one of the boxes for the home office. So I ask my movers to go retrieve those boxes from the truck. So they retrieve 5 boxes. That is the equivalent of 5 physical reads. But then once they bring those boxes to me in my home office, I must open up those boxes and search through each one of those boxes in order to find my laptop charger. And those are an additional 5 logical reads. Okay? So now I'm standing, and eventually I find that thing. So now I'm standing in my room, and I have 5 boxes in here, all the boxes for my home office. But then I realize I need something else, and that something else could either be in the boxes in my home office, or maybe they're also in the boxes for my library. I'm not sure which, so I need to scan both. Well, I already have the boxes for my home office in the room with me. However, my movers must now go back out to the truck to get the boxes for my library, retrieve those. And that's another 3 physical reads. However, once I have all of those boxes, I must do a total of 8 logical reads because I must rescan the 5 boxes for my home office in addition to the 3 boxes that were given to me. So at any given point in time, the boxes that I may need may be in the room with me, aka in the buffer pool, but there may be a chance that they're not and they're on the truck. So are physical reads necessarily representative of the total amount of work that we have to do? No, but logical reads are, and that's what I'm attempting to convey to you here. So some key takeaways, which is the item that I just summarized here, that physical reads are effectively a subset of the total logical reads, and the total logical reads will tell me how much work the query really had to do in sum total. And that remember that all work is executed against data pages in the buffer pool. So, I couldn't just have the movers read those boxes or scan those boxes as they brought them in. They had to bring them to me in the buffer pool, and then I had to scan all of them. So it's additional work essentially, right? And keep in mind that this cost compounds itself when you're in the cloud. Many of us are either moving to hybrid scenarios or moving fully up to either Azure or AWS. And of course, in the cloud, we pay for compute. And what do you think spends its time scanning those boxes for us? The CPU. So the more I/O I wind up doing behind the scenes, the more CPU that's going to cost me in the end. So it's in my best benefit to reduce the amount of I/O that my queries have to do behind the scenes if I want to reduce my compute. And if I can reduce my compute, I can reduce my costs in the cloud. Okay, next chapter, internals. Let's talk a little bit about data structures. So just get me one record. Sometimes people give me a simple query like, select top 1. So we're just pulling back one record. So do you think the storage engine, when it executes this query, is really just going to retrieve one single record? The answer is no. The smallest unit of work that SQL Server can do is something called a data page. And a data page is an 8 kilobyte construct that's comprised of these 3 different components. Think of this as equivalent to a box, right? So my movers, if we go back to the analogy, cannot just retrieve one single element for me. They can only work in units of boxes, right? And that's why I like to think of data pages as a fixed size box, an 8 kilobyte box in this particular case. So again, that is the smallest unit of I/O that SQL Server can do. And a collection of data pages is a table, right? So, I have a create table, my table, and this, in this particular form, with this particular declaration, is materialized in SQL Server as a heap, which is just a linked list of data pages. It's all completely unordered data. Unordered, okay? I want to be very, very specific about that. So that's like having a whole bunch of different boxes, but we don't really have an idea of what's in them. I know that they are all the objects from my home office, but they're all scattered inside a box wherever they happen to fit, okay? Now, let's pretend I wanted to instill some order here. So in this case, I'm now going to add a clustered index to my table. And what that does is that instead of a heap, that'll transform that heap into something called the B tree, which stands for balanced tree, not binary tree. And this balanced tree structure is essentially our table. It's the clustered index. The heap no longer exists. It gets rebuilt and rematerialized as this. Also, all non-clustered indexes also take the form of the B tree structure. And this is kind of what it looks like from a high level. All right. So let's take a deeper dive into what these heaps and B-tree structures happen to look like, and let's talk about how SQL Server and the storage engine navigates through them in order to find our data. So the thing about T-SQL is that there's a how versus what. Well, what do I mean by that? It's the nature of the T-SQL language. T-SQL is a declarative language where you're saying to the query optimizer, what is it that I want? Tell me, you're going to tell the query optimizer what it is that you want, as opposed to how to get it. You're not giving the query optimizer actual instructions. Instead, the query optimizer's job is to come up with the execution plan. And it's inside the execution plan where you have, where you dictate the index seeks, the index scans, the nested loop joins, and those types of things. You don't dictate that in your T-SQL code, unless you're cheating and using hints, but that's typically not the case. Typically, this is, again, you're leaving the task up to the query optimizer. So this is a declarative language, and it differs from many of the other programming languages that we're used to, which are procedural or imperative programming languages, where the code dictates how to do things. Think of it like, C, C++, Java, C Sharp. Those are all procedural or imperative programming languages. But you got to remember that T-SQL is different. It's a different class of programming language. And because of that, that has interesting key consequences for us. In this case, the fact that the query optimizer is the one that comes up with the actual execution plan, the true execution plan. So actual is a bit of an overloaded word in this particular case. In either case, let's talk a bit about what things look like. And for the next handful of slides, we're going to use this customer table as our example. So right now we have this customer table. It has a bunch of different typical data points, but notice that there's no clustering key on this. Because there's no clustering key on this, this is materialized as a heap. And you can see a handful of different sample data points in here. Now, this is all unordered data, right? So I don't know where anything is. Now, if I want to add some order to this, I'm going to add in a customer ID auto-incrementing column here. Or it's an auto-incrementing int, I should say, and it's the primary key, and I also added that as the clustering key, so it's that you can see that definition up at the top. And then I've also added in a non-clustered index on last name and first name are my two index keys, and I'm including two additional columns, the first visit and email. Okay, so for the next couple of slides, we're actually just going to focus on the non-clustered index, but a lot of this will also apply to the clustered index as well. So let's look at the B tree structure of this non-clustered index. I have the root level, which is the topmost node. I have 0 or more, in this case just one, intermediate levels or non-leaf nodes. And then finally we have the leaf level, or all of the leaf nodes at the bottom, right? So let's take a closer look inside of what each of these look like. So the root level. In this case, here are 3 sample data elements, which have a copy of my first name, last name, and then a number after that. That's the customer ID, the clustering key. This is essentially a pointer back to my clustered index. Now, this is not every single piece of data I happen to have, right? It's just 3 different particular values. But the 3 values in here are very important because these play into the intermediate level. So here's a subset of the intermediate level. And notice that the first value inside the root level, Adams James, is also the first value inside the first intermediate level data page. And then the second value in the root level is the first value in the next intermediate level data page. So these are essentially pointers. So we can use these to navigate. So if I'm looking for someone with a last name that begins, that's between the Adams and Martinez, maybe it begins with the letter D, as in Dominic, for example, I know that I need to now navigate to that first leaf level page, not to the second, because Dominic is between Adams and Martinez. All right. And then when we look at the first intermediate level page and then the leaf level underneath it, we see that we follow a similar pattern where Adams James, that first value, is now a pointer to that first leaf level page, and then Chavez Esme is a pointer to that second data page first value as well. Now notice on the leaf level, there's additional data points. In addition to the clustering key, there's also first visit and email, my included columns. So my included columns play no role as far as navigating the B tree is concerned. So they can't help me if I'm doing a seek or scan against those different data points, but they're now available to me in case I needed those as part of my query. I don't necessarily have to jump back to the clustered index to retrieve additional data points. We include a copy of them here, and you'll understand the performance consequence of this shortly. Okay, so let's talk about querying these different constructs. So first of all, we have a simple select statement from customer where last name is equal to Dean. Well, how am I supposed to find that if we happen to have a heap in front of us? This is all unordered data. So unfortunately, I must scan the entire heap. Even if I were to find a record where last name is equal to Dean on the first data page, there may be many more because there's no constraints on this table dictating that a given record is unique or anything like that, right? So I must scan this entire thing. And from a costing perspective, let's talk about logical reads. One logical read one logical read is the number of data pages I had to read. So so if I did one logical read, that means I read one data page. So in this simplistic example, I've now read 8 data pages. Now, on the other hand, let's take a look at a non-clustered index like the one that we were looking at earlier. So if I have this select statement without a predicate, I must do what's called an index scan. But with a B tree structure, I must always start at the root node, and then I go to the first intermediate level, and then I go down to the first leaf level, and then I can scan across. I can't just jump down to the first leaf level data page. I must always navigate the B tree in a B tree structure scenario. So in this case, number of logical reads is actually 10 data pages for the identical data. So it's actually a little bit of extra work in this simplistic example, another 2 data pages worth of I/O. However, the advantage of having a non-clustered index is the capability to do an index seek operation. So I've added in a predicate where last name is equal to Dean. And now I can look to see at the root level, well, Dean is between Adams and Martinez, so I need to navigate down to this intermediate level data page, and I see that Dean is between Chavez and Howard, so I know to navigate to this leaf level page, and I'm done. In this case, only 3 data pages worth of logical reads. That's a heck of a lot less than 10, a huge significance. And this is a perfect example as to why seeking is a very, very efficient operation. We want to seek if we can. Now this is a different variation where last name is greater than Inez and last name is less than Sark. Do you think that SQL Server is going to seek or it's going to scan here? Well, the correct answer is that it's essentially going to do a little bit of both. So first we're going to seek on the first value, Inez. So we seek down here to this particular data page, and then we do what's called a range scan all the way up until we reach Sark. Or we could actually have to go to the end of the structure. But in either case, we only do a partial scan here, or what's called, again, a range scan. So in this case, this is more efficient. I'm able to seek to what I need to and then scan across the rest. And in this case, this only cost me 6 data pages. And that's a good thing too, leveraging the order of the non-clustered index here. Now, what if I wanted to find first name is equal to Arthur? Do I really know where Arthur happens to be here? Can I navigate to that? The answer is no, because this B tree structure has been defined by the last name. How can I actually navigate this tree because no last name has been defined? So unfortunately, in this particular example, I must do a full index scan, which once again costs me 10 data pages. Okay? So this is where the notion of key order matters dramatically. If there's a scenario where searching by first name is a very, very common scenario in my workload, I may want to consider a second non-clustered index where the leading key is first name. May. Again, that's a bit of a separate topic, but understand that that's why this is important. Okay? Now, are seeks always better than scans? That's something I oftentimes hear from folks who don't really fully appreciate or understand the internals of the storage engine. And there's a lot of ways that seeks can actually be worse than just a full-blown scan. And this pattern here is one of those. So in this case, we're looking for 6 different individual last names. So I'm going to seek on the first last name. But then I'm also going to seek on the second last name, and the third last name, and the fourth last name, and the fifth, and then the sixth. And as you can see here, every single time I seek, I must navigate the full B tree structure. And as you might imagine, this is a heck of a lot more costly at 18 data pages. Whereas just doing a full index scan would have been faster and more efficient at 10 data pages. And this is a key reason why sometimes you're just going to see a scan rather than a bunch of different seeks. Or this is why I also hate hearing from people that whenever they see a scan inside an execution plan, they must try and figure out a way to turn it into a seek. No, do not do that, because again, there are scenarios such as this one, and that's not uncommon, where you're actually better off just doing a full scan. Okay? Finally, let's talk about the key lookup operation. This is one of those kind of nefarious performance killers here. So notice that I've made a slight adjustment to the select statement, the columns that I wanted. We're looking for first name, last name, first visit, but we're also looking for the city and the state that this customer resides in. Was city and state part of our non-clustered index? No. So where are we going to be able to get that? Well, we would have to go back to the base table. So in this case, I do have a predicate that would allow me to seek here where the last name is equal to Huang. So I'm going to go find that last name. I find that particular record. But again, I still need 2 extra data points, city and state. So I'm going to use the clustering key as a pointer to now go back to the clustered index to retrieve the value that I need to get those additional data points, because we did not include city and state in this non-clustered index. This key lookup operation is extra I/O and extra work here. Now imagine if we had to do this, several hundred times individually, because we had a similar pattern to the prior where we did a bunch of singleton seeks that were not against a non-clustered index that were not fully covering. I would have to do a multitude of key lookup operations, and that is not very efficient at all. So keep this in mind as yet another thing that can really kill performance. So let's do a little bit of recap. So hopefully you now have a better understanding of why index key orders matters, because it directly affects our capability to seek versus scan against a non-clustered index. And hopefully you have a better appreciation as to why included columns can really help a query. It allows us to avoid that key lookup, that additional bit of I/O. And hopefully you now have a better appreciation of why seeks are not necessarily better than scans. And you should always check the properties inside the execution plan, and that's what's going to tell you the number of seeks. If you happen to see a seek operator, if you happen to have executed it multiple times over, as opposed to just one single time. Okay, so with that, let's switch gears and now dive into demo. All right, let's start off with our overview demo. So first of all, I'm going to be using a demo database called Auto Dealership Demo, and this is available up on my GitHub. And then I'm also going to turn on actual execution plan. And then we're going to use 2 different commands here. First is drop clean buffers. That's just going to blow away everything in the buffer pool so that we start with a cold cache. And then I'm going to make use of set statistics IO on. This is a command that I advocate for heavily, because I'll have people tell me that, oh, this query wasn't expensive. It only returned 5 records or 500 records, a small amount, right? But for all you know, it had to process maybe 500 gigs worth of data behind the scenes, right? So set IO is going to give us that IO information about what this query really truly did behind the scenes. So first of all, let's start off with a simple example of reading from a cold cache. I'm going to select top 100,000 from inventory flat. And then if we first look at the execution plan, we see that this did a clustered index scan. So it's just a full scan of this particular table, the inventory flat. In this case, we read back 100,000 records. Nothing too special about that. As far as IO is concerned, we had 1977 logical reads. However, what's interesting is that we only had one physical read and actually a whole bunch of read-ahead reads. So SQL Server actually did more I/O from a physical side because we started on a cold cache. But in this case, this is actually okay because read-ahead reads are actually a very, very, very efficient operation. So I'm not going to get into the nuance of what a read-ahead read happens to actually look like. Just understand that we really just had to do one physical, and the optimizer basically said, or actually it's the storage engine, I'm sorry. The storage engine said, you know what, I think we're going to need more, so I'm going to grab all this other stuff preemptively. It's like the movers going back out to my truck instead of saying, okay, Andy says he wanted, the 5 boxes from the home office, but I think he may want the boxes from the home office and possibly the library as well. So let's just grab those while we're out here. That's essentially what's going on with this read-ahead read mechanism. But in the end, the query only needed 1,977 data pages in order to fulfill my query. Hence, that is the true number of logical reads here. Okay? So if I were to repeat that once more, now we're no longer on a cold cache, right? However, if I look at the execution plan looks the same. The reason I point this out is that the execution plan does not care whether data is on disk or in the buffer pool. That is part of the job of the buffer manager within the storage engine. Remember that slide from earlier on. So the query optimizer, when it comes up with the execution plan, has no knowledge of that, nor does it actually care. That responsibility to figure out where a data page resides is on the buffer manager. Now, if we go look at the messages tab once again, logical reads, once again, it's the same 1977. However, in this case, the data pages are in the buffer pool already, so I have 0 physical reads. Okay, and this is actually kind of what we typically will be seeing. So what's actually inside the buffer pool? There's a cool bit of diagnostic code right here that I will share with you. And now this is going to show us that, yeah, we're using data for the auto dealership demo, about 55 megs worth. There's also utilization of TempDB for other things. And as you can see, there's other databases in here. They're using trivial amounts of within the buffer pool. And this not only includes data pages, but it also includes metadata information and other supporting types of pages and information. So I'm going to drop clean buffers to flush everything out, and then we'll look inside what's in the buffer pool once again, and you'll see that pretty much everything is gone, but I mean, there's still trace elements of data left in here, and again, that's metadata information as opposed to data pages inside the buffer pool. Okay? So let's do a simple mixed join example. This kind of goes back to our example from earlier. So I'm going to do a select from sales history inner join customer, and then I'll do a second select from sales history inner join inventory. This is similar to the table 1, table 2, table 1, table 3. I just want to do this quick simple example just to again drive home the point of how the buffer manager works and the behaviors behind the scenes. Okay, so in the first query, we have to read everything from disk. So we get some physical reads, and we wind up getting a bunch of read-ahead reads as well. And then here's my total logical reads. However, once we come down to that second query with the inventory sales history, we have the same number of logical reads, but we have no physical reads once again because those data pages were already pulled into the buffer pool from the prior statement. Otherwise, the other table, we happen to have both physical reads and read-ahead reads in this particular example. So you see how, again, we have to do some physical, but again, in this case, there were already some data pages already in the buffer pool. So let's explore some actual query operations. I'm going to turn set statistics IO on once again. And then we're going to take a look at 2 different tables called sales summary. One's called sales summary heap, which of course is the heap version of it. And then the other one is just sales summary. I'm just going to do a quick select star just so you can get an idea or sampling of the data that's inside these 2 particular tables. And then we'll take a quick glance at the execution plan and the underlying IO for each of these. So each of these different tables have 500,000 records inside of them, okay? And if I look at the execution plan, of course, the first one is a table scan operation against my heap, and the other one is a clustered index scan against the table that has a clustered index against it, okay? And then from the messages perspective, we see that the heap took 3106 logical reads, as opposed to the clustered index, which actually took a little bit of extra. So this is a simplistic example of how we have to do just a little bit of extra work because we have to navigate the B tree, and there's actually some metadata that we have to look up in index allocation pages, essentially. But that's kind of a side detail that's not really pertinent to this. Just understand that there's a little bit of extra work that we happen to have to do when you're querying into a clustered index versus a heap. But of course, typically we're not running queries without a predicate, right? So, oh yeah, let me first show you what the difference looks like if I were to simply just do a select top one, okay? So if I were to do a select top one, we still have to do a table scan and an index seek, but we have a top operator that limits the output. And then if I go to the messages tab, we only have to do one logical read against the heap, and here we have to do three logical reads because we have to look at that index allocation page, and then we have to navigate the B tree. Okay, so that's what that happens to look like. So again, a little bit of extra work. However, typically when we're querying our tables, we have predicates, we have join predicates and things of that nature, right? So in this case, I'm going to do a select statement with a VIN number, which is a vehicle identification number. That's what VIN stands for. And now we have a much different set of behaviors. In the case of the heap, I still have to do a full table scan, whereas in the case of the clustered index, because it happened to be clustered on the VIN number, I now get a clustered index seek. And if I look at the underlying I/O, this is where I see the tremendous difference. Of course, this is the full scan where I had to read through everything, but in this case, I was able to seek on that specific value. So this is where the advantages of having indexes and clustering start coming into play. We're able to get these, really nice seek operations and greatly reduce the amount of I/O that we happen to need behind the scenes. So let's see. So in order to help get you some information about these different elements, there's a couple of different, or there's one particular store procedure that's built into SQL Server that I really love to make mention of, and it's called SP help. So this is a system store procedure, and you can run this against your different tables. And this is going to give you underlying information about that particular entity. So at a quick glance, I can quickly see that, the first table, sales summary, happens to have a clustered index on VIN, and it has a non-clustered index on the transaction date. I can also see the underlying data types and the columns and other information about that. And then if I were to scroll further down into the second result set, I'd see information on sales summary heap, see that there is a non-clustered index on the transaction date, but otherwise there is no clustering key, of course, because this is a heap after all, right? So again, use this to get quick information about what's going on, to have that at your fingertips whenever you need to double check yourself as far as, well, what's inside my different tables and stuff. All right, so let's do a quick range scan example. So we're going to select sold price from inventory flat, where sold price is between these two values, 30,000 and 31.99. I'm also going to use option max stop one just to prevent parallelism from occurring in this particular simple example. So if we look at the corresponding execution plan, I happen to have an index seek operation here. And then if I were to look at the seek predicates, we notice that we have the seek keys start and end. So my starting value of 300,000 and my ending value of 31.99. But there's more information to this execution plan. If I were to open up the Properties tab, so I'm going to hit F4 to pop open the Properties tab. I'm going to select my index seek, and then I'm going to look at seek predicates, and we'll see that additional level of detail down here. So here's my starting values and my ending values down here. And then if I were to fully expand all this out, you would see the full detail with the full values in here as well. We also see scan direction. I happen to do a range scan, and we scanned forward in the non-clustered index because, and this is actually quite important because as you'll see in this next example, which I'm not going to do, if I had specified order by sold price descending, we can do something called the reverse range scan, where we will will seek on 3199 and scan backwards. So this is a cool little nuance and trick of leveraging the ordering that is presented to you by your non-clustered index to potentially order data in the complete opposite fashion without having to do a sort operator. But again, I'm going to skip this. You can run this guy on your own. This is the example that I really want to kind of talk about here. So we're doing a query against sales history in the customer table where the customer state is in one of these 4 different values. These are 4 different states here in the United States, okay? So we're just going to run this guy here. And let's take a look at the corresponding execution plan. So in the execution plan, I don't have any seeks of any sort. We're doing scans against the customer table here. It's a full, a full clustered index scan here, and the corresponding cost for this is 15,750 logical reads. And of course, the reason that we wound up doing a full index scan is that there's no non-clustered indexes on this guy. So I'm going to create a non-clustered index on the state just to help out this query. And now let's repeat and see how this behavior differs. So I've executed this, and let's look at the execution plan. Fantastic. We now have an index seek against the customer table. However, we didn't do one single seek, did we? That's an interesting question. So what you really want to look at is how many times we actually went into this, like, or is this a range, a range seek, for example. So instead, I'm actually going to go out to the properties, which would be the easiest way to tell, and then seek predicates. Let me expand this all the way. That'll do. So notice that in seek predicates, this is actually showing me that we did multiple seeks. We seeked into this 4 different times because we had 4 different state values. So this is the, ooh, hey, wait a minute. We did a bit of extra work that we didn't quite expect. And you can also see this in set statistics IO where against the customer table here, we did 486 logical reads. So that's actually still really good. It's a heck of a lot better than the 15,000 originally. But then we have the scan count here. I dislike the word scan in this output. It's kind of a misnomer. This is more just like the number of operations or the number of times we had to access the customer table, whether it be a seek or a scan. So again, this is further evidence that we went into this guy 4 different times. Okay, so here's where you find those hints of repetitive access. So just as a baseline, let's see what this happens to look like if I only query with one single state. So this is our best case scenario. I have an execution plan. I have a single index seek here. I'm not going to bother opening up the properties tab. But if you look at the customer table here, scan count 1, 288 logical reads. That's pretty good. Okay. So instead of our best case scenario, one single state, what if we happen to have a query that happens to look like this? Keep in mind that in the United States, there are only 50 discrete states, and you see that list of states here in the in clause here. I've seen this kind of code generated by ORM-based workloads, whether it be something like Entity Framework or NHibernate. And this is extremely inefficient because had a human who knew the United States written this, they would know that this where clause is completely worthless. We're going to scan everything, right? Because we're inclusive of all 50 states. However, ORM does not happen to know that. So an ORM is going to generate code like this. And based upon what we've learned so far, can you imagine what's going to happen next? Well, let me execute this and you'll see. So if I were to look at the execution plan, I have index seeks once again, but what happens if I look at the details? Because a lot of people don't look at the details. And let's look at the seek predicates and the number of seek predicates that we happen to have here. And you see quite a few of them, right? So this is a case where we happen to query into the customer table repeatedly and completely unnecessarily. If we look at the customer table, scan count 50, and we've completely bloated out our number of logical reads, 1808 in this particular case. What would the equivalent IO be if we had just done a complete scan of the customer table? Well, I can show that to you here just by doing a select state from customer. Instead of 1808 logical reads, a simple scan of the customer table by state is only 1606. That's a savings of just over 200 logical reads. But think of it in terms of percentages. That's a non-trivial percentage difference as well. Okay, so let me just quickly clean this up a bit. So I have a different optional multi-seq variation down here, so do take some time to check that out. And there's actually a couple of other additional optional demos here as well. So take some time to check those out a little bit later. But let's continue on, and I want to go into some specific scenarios now. So scenario number one. Okay, going to turn actual execution plan and complete my additional setup here. Okay, so example number one, we have a select of some different data points from 3 different tables, inventory, sales history, and customer, where the VIN number happens to be equal to that particular VIN number. I'm going to use an in clause once again. Okay, so if we take a look at this base query, let's look at the execution plan. The execution plan happens to have in index seek, but it also happens to have my good friend, the key lookup operation. We happen to do a little bit of extra work here. Well, what did we have to go find? So if I go look at the key lookup here, the output list. So these are the different data points that we also needed out of that particular non-clustered index, but they weren't in there, so we had to go back to the base table in order to get them. Okay. And oh yeah, what does that look like from a IO perspective? So in this case, we'll just total them up just to do an approximation, 366, so about 16 logical reads. Not too terrible, right? That's kind of our best case scenario with just one VIN number. But what if I happen to have multiple VIN numbers here? So again, this is another example of like what might happen if you happen to have ORM-based code. Again, this is an anti-pattern that I see on a regular basis, even from written by people. Sometimes people will just copy and paste discrete values into like out of an Excel document and put them into here or something like that, right? So we still have index seeks and key lookups, as you'll see here in the execution plan. However, because of the repetitious behavior, my IO increases dramatically because we have to do multiple scans, or really multiple seeks. So we're doing multiple accesses into these different data elements, or data tables, I should say, and the amount of IO required increases dramatically versus the 3, 6, and 6. It's now a heck of a lot higher. I mean, these are still relatively low numbers, but keep in mind that these things add up. They add up quickly over time. So let's add some covering indexes, and to help you deal with the indexes and such, we have another built-in stored procedure called SP-help index. That's built into SQL Server, and that'll give me some information about what indexes exist on a given table, like the inventory table. However, it's only showing me the index keys. It doesn't tell me if I happen to have any included columns here. So that's actually the reason why I dislike using the built-in SP-help index. Instead, I personally advocate and like to use a version of SP-help index written by Kimberly Tripp of SQL Skills. So her version is fantastic, and you can just Google for those keywords and you'll find it really quickly. In either case, not only does this give me index key information, it also includes included columns in addition to other data points like the filter definition and so on and so forth, right? So in this case, I know now what non-clustered indexes I happen to have on this table and what included columns, if any of those non-clustered indexes happen to have. So I'm going to create a couple of non-clustered indexes, one on the inventory table, one on the sales history table, to address my 2 key lookup operations that were occurring in that particular example. And then while that's finished running, which it just has, let's rerun our above examples. I'm going to run the base version and then the singleton version. Yep, or the multi version. In either case. So notice that in our best case scenario of just one VIN number, instead of 6 logical reads each, I'm now doing 3 logical reads. And notice the dramatic reduction in I/O here. So this has also been reduced. This is fantastic. So, and again, it's only a few hundred logical reads, but think in terms of percentages. How much percentage did we reduce? More than half, actually. So that's a fantastic thing. So you might be thinking to yourself, who cares about this? I mean, this is all trivial. These queries are running in less than a second. Why do I really care about this? The thing is that a lot of us are stuck in the mentality of only concerning ourselves with that big, bad, single nasty query and troubleshooting the single heavy hitters. What we don't necessarily pay attention to are the very fast queries that are run in high volume by our workloads, which they may run really, really fast when you run them independently, but they still have some inefficiencies in them, like these hidden keylookup operations. And it's the underlying I/O that can build up over time because maybe you have a select statement that's run by your application hundreds or thousands of times a minute. That I/O, that cost behind the scenes, will add up and add up rapidly. So I have this example store procedure here, which is basically a materialization um, of that prior example. And then I'm going to rerun this in another window. I've actually already done that earlier on. And then, this is something that just runs really, really fast. I'm just going to actually just run it real fast right now, just so you can kind of see, hey, here's one simple quick execution of it. You see that it runs in less than a second. But if I ran it 1,000 or several thousand times, what would this really look like from a resource utilization perspective in bulk? And to show you that, I'm actually going to cheat and use SentryOne. Yeah, I work for SentryOne, and this is not meant to be a sales pitch by any means. I'm just being lazy because it's the easiest way for me to show this information to you. But you can look this up in Query Store or whatever else. In either case, this is where we are showing you historical information about query executions and such. There we go. So I happen to have 2 statements in my random VIN lookup batch, an insert and a select statement. I actually ran this guy 3,000 times, or ran that sample batch a couple of times over. But look at the total I/O, well over 100 million logical reads. Even though the total duration was relatively trivial, all of these individual executions run really, really fast. You saw how I ran this earlier, right? A single execution ran in a fraction of a second. But again, because my workload runs this in tremendous volume, I really, really get hurt. And if you look at the preview of the plan diagram, you see that we have 2 keylookup operations right here. So again, this is one of those cases where you need to look at things from a workload perspective, take a bigger picture view of what's going on, because if I can drop this down by eliminating the keylookups, I can reduce this by well over half. And again, that adds up really fast. Wouldn't it be nice to say I've reduced this down to 40 million logical reads in sum total rather than over 100 million logical reads? And again, this is only over a couple of minutes and a handful, only a few thousand executions. What would this look like over multiple hours or a full work day, for example, right? So all sorts of things to keep in mind, but keep in mind that you need to look at things not only from that singleton, big query perspective, but you also need to look at things from that workload perspective. What happens in the bigger picture? What happens at the sum of all totals? Okay. All right. So I'm just going to do a quick bit of cleanup here, and then we'll move on to the next scenario. Okay, scenario number 2. Let's use our auto dealership demo once again. I'm going to do a little bit of setup here. I'm just going to create a couple of demo indexes, and I'm going to turn on set statistics IO and set statistics time, so that way we can actually see how much time SQL Server is spending on our queries. Turning on actual execution plan, and now we have a a couple of different variables that we're declaring: transaction date start and end with the date time data type, and then state, which is just declaring as an end char 2, and then we're going to do some select out of that, out of the different base tables, and where transaction date is greater than the start and less than the end, and the customer state is equal to the state, right? Similar kind of thing that we saw before. So remember, I created some covering indexes to help support everything, right? So we should be getting nice clean seeks out of this. However, if I look at my execution plan, particularly at the customer table, we see that I get an index scan here. Well, wait a minute. I created a nice non-clustered index against, against the customer table that should help me get a seek. Why am I getting a scan? This is another common kind of question that many of us will get. What's happening here? Well, we get our first hint when we look at the select statement and the select operator. There's a little warning symbol on top of it, and when I highlight that warning symbol, I can read the little tooltip, and at the bottom it says that we have an implicit conversion that's going on here, which may affect the capability to do a seek. So this is an example of how we're getting burned. So what I'm going to do here is I'm going to look at the customer table, and then I'm going to use a keyboard shortcut in order to actually double check what's inside this particular table. I'm going to hit Control 3, and this actually executes SP help. This is actually a really cool thing. Remember how I introduced SP help to you earlier? Well, if you actually go up to within Management Studio up to Tools and Options, keyboard query shortcuts, you can actually assign these different commands to different hotkeys, as you can see that I've done here. These are some of my favorite ones. So if I ever quickly need to double check, what indexes are in a given table, I can just highlight that and hit Control 5. Or in this case, I'm just going to hit Control 3 just to see something else. In this case, I want to look at the underlying data types, right? Because the customer table, in this case, is defined as a char2. Whereas if you remember correctly, I created a variable nchar2. The n, of course, means that that variable can contain Unicode information, whereas the table itself contains non-Unicode information. It's not an N char, it's just a regular char. Because of this data type mismatch, we have to convert the different data types. These look like characters to us, but to SQL Server, the underlying data is completely different. So therefore, SQL Server will use something called the data type precedence chart and take the lower of the two data types and convert that one. Now, in this case, the lower of the two data types is the state column inside the customer table. So unfortunately, what SQL Server must do in the execution plan is it must scan the entire thing. I'm sorry, this is the execution plan for SB help. But if we were looking at the prior execution plan, it must scan the entire customer table, up convert every single state value, and then we can do our comparison. So there's a huge difference here as far as the amount of work that needs to be done. And this is why it's important to match your data types and to double check that. If you've been following me for years now, you'll know that my very first presentation as a speaker was all about data types. So I spend a lot more time talking about this particular topic and why your data type choices matter. You can go look that up on the internet. There's recordings of that older session out there. In either case, let's take the time to properly match our data types. I've selected a state now, a state as char2, and let's compare and contrast. And now if I look at my execution plan against the customer table, I now have a nice index seek operation. So this is cool. And of course, if we were looking at messages tab, we'll see that the IO is much more reduced, 288 logical reads, as opposed to the prior one. I forgot to look that up, but we already know that the customer table is a much larger table. And we already saw earlier that it's a heck of a lot more than 288 logical reads when we do a full scan on the customer table. Okay, so in either case. Now, how do I find out if I happen to have implicit conversions already going on in my code? This is where Jonathan Cahias of SQLskills.com can come to the rescue. He's written a phenomenal blog post that also happens to have some code that will shred the plan cache and shred the XML inside your plan cache to help you determine and find all of that. So I'm just going to run a quick bit of this here. And in this case, you'll see some output. So we see the corresponding statement, we see the columns that were in play, and we see that we converted from a char to an nchar. And then I can even pop open the execution plan here to view the execution plan. For what it's worth, a lot of cases, you may dodge a bullet, if you will, and not suffer from an implicit conversion if the Variable happen to be the smaller of the two data types. So you only have to upconvert a single value, the variable, right? And this is also really, really important when you happen to have either dynamic SQL or ORM-based T-SQL as well. I find a lot of app developers don't necessarily appreciate the nuance of the data types and will mismatch the data types in their T-SQL or in their code, such that when it generates T-SQL, it'll generate non-matching data types, right? So again, I often find that mismatched data types and implicit conversions is a huge performance killer in ORM-based workloads because again, developers don't have a good appreciation of why your data type choices matter within SQL Server. All right, so that concludes this particular demo. Just going to do a quick bit of cleanup, and then we're going to move to the final scenarios. You'll see that this is actually labeled as scenario 1 and 2. There are scenarios 3 and 4. Those are up on my GitHub. I don't have time for that. That's usually saved for a 75 or a 90-minute session. But instead, I want to jump to scenario number 5. This is a relatively new scenario that I really like. So the setup or the scenario is we happen to have a developer who says, you know what, maybe we have a large volume of data, right? And they think it's more efficient to try and find and retrieve only the IDs, like the keys of what we need, and then go back to the same table once again in order to get the rest of the subsequent data. This is particularly the case if you happen to have very large, very wide tables. I've seen that type of thing before, but there's a lot of folks again who don't understand the internals of SQL Server who seem to think that this is a more efficient approach. But now, if you leverage all the things that we've learned today, you should already be predicting kind of some of the things that are going to happen and should hopefully be able to predict why this is going to be a terrible approach. So let's first introduce the example data. I'm going to use my big horizontal and flat table called inventory flat. We're going to look at model names of vehicles, and we're going to look at I'm going to show you the count of them. And then the sum total count of number of records. So each different model in here has approximately 150 to 160, give or take, records. So it's relatively balanced is what I'm trying to show you in this bit. And in sum total, there's about 2 million records total, okay? And then here's a list of the supporting indexes and non-clustered indexes that happen to be here. The key takeaway is that we do have a index key on the model name with the included columns of the clustering key, inventory flat ID, and the VIN number here as well. Okay. All right, so we happen to have an example query here where, I'm going to be selecting a whole bunch of different columns. But again, part of it is that, pretend that this is a much wider column. So there's a whole bunch of different columns that we have to bring back. Maybe it's like a reporting data warehouse or something like that. So this is our inefficient scenario. So I want to turn on actual execution plan. And then we're just going to get everything from that inventory table where the model name is equal to RAV4. So remember, all of the different models have approximately the same number of records, give or take a small percentage variance. So inside the execution plan, we do a full clustered index scan. So we go through the entire table. And if I look at the logical reads, we did just short of 40,000 logical reads. So 39,500, and my statistics time information is showing me that we did, 3,800 milliseconds of, or that was the total elapsed time for this particular query. Okay, so this is my baseline. So again, I have that person who comes along and says, you know what, we should split these up into multiple queries. We should only go into this table, get all the IDs for all of a given model name, and then we should go back to that table once again to get everything else. Because, it's inefficient to scan the entire table, right? So let's retrieve the IDs first, then run that second query against the Y table to get all of the columns. So that's what this looks like. So I'm going to create a table called temp IDs. I'm going to cluster the temp ID, so that will be my clustering key and primary key. We're going to insert the clustering key IDs, which is the inventory flat ID out of inventory flat, where model name is equal to RAV4. And then we're going to go back and, against inventory flat, interjoin that against temp IDs against my key in order to get the ultimate, full data back here. And again, those of you who have been paying attention should know exactly what's about to happen here. So let's see how much work we did. So if we look at the execution plan, we did a quick little index seek, and then because the thing is, I did have that non-clustered index, so that's something that helped me out here. I didn't have to go against the base table because I was able to do that non-clustered index seek. I happened to do less I/O, and because remember, in that first operation, I only needed the clustering key, which is implicitly part of my non-clustered index. Remember the B tree structure that we saw earlier? That's how SQL Server is capable of being able to jump back and do a key lookup because a clustering key comes along for the ride. It's implicitly included in my non-clustered indexes. So again, we have a non-clustered index seek here, but then are we even making use of indexes seek here? No, we're doing full index scans here against the base table and then against my temporary table as well. But let's look at the total I/O. 596 logical reads plus 39,000, yeah, it's 596 plus 39,571. Once again, I did that full table scan once again. Plus, I had to do additional logical reads against that temporary table that we created, 221 logical reads. So we actually did more I/O here. And of course, you should understand why. Remember, SQL Server must, query when it's querying the base table. It must, only retrieves the full data pages here, right? I can't just retrieve some of the records, right? And there's no capability to do range scans because we don't know, we're looking at an auto-incrementing ID here. So there's no way to do an individual range scan. I don't know where those IDs are gonna happen to be. They could be split out all over the place. The ones that correspond to the RAV4, right? What was my total execution time? 2,500 milliseconds. That was, what was the other one? I forgot already. So in this case, this actually did wind up being a little bit faster at the trade-off of, again, being a little bit of extra work here. So is that something that we really want to be trading off? Well, again, remember, what if this is a workload that, does things a whole heck of a lot? What if this table was even wider, representative of that crazy data warehouse table that has, 100 columns or something like that, right? That's actually the more common scenario that I see this. I can try this with an exists instead of an inner join. Let's see if that happens to help things or not. Some people will say, I shouldn't have done a join, but here's the thing. You come up with the same execution plan anyway, unfortunately. And if I look at the messages tab, I have a similar kind of I/O as well. So, 39,571 here. Okay. So this is a different optional example of, going parallel. We can try to see if parallelism will help this out or not, so try that one out on your own. But in either case, hopefully you have a better appreciation of why that particular anti-pattern really isn't the best idea. Okay. So with that, let's wrap things back up. So I want to leave you with some parting thoughts. I want to encourage you to widen your perspective. You remember I made the point earlier about how a lot of folks will only focus on that singleton heavy-hitting query. Well, instead of that, start thinking about your workload. What happens from that workload perspective? The other thing to think about and keep in mind is that the buffer pool is a shared resource, and you are not the only database on that SQL server most of the time. So, most of the time, our database resides on a SQL server with many other databases. So they all have their own workload. The buffer pool is shared amongst everyone. You need to be conscious and aware of that as well, which is exactly my second point right here. And please try and be mindful of unseen work being done to fulfill a query. Again, this comes back to the simple example. Maybe I have a select statement that only comes back with one record, but I may have to process gigabytes and gigabytes and gigabytes of data behind the scenes. So be conscious of the work that happens behind the scenes because all of that adds up, even if your execution time could be really, really fast. So with that, this is where I'm going to, actually, because this is pre-recorded, there will be a live Q&A after this particular presentation. But again, here's my GitHub URL where you're going to be able to find repositories with my decks, my slide decks, my sample queries and such, and my demo database. Of course, my contact information is in the lower left-hand corner there for you. And with that, I do want to say thank you so much for joining me today. And now I guess we are going to switch over to the live Q&A. Thank you for having me. It's been a pleasure. I hope you've enjoyed this presentation.